Good morning, dear students. Today we continue with our module entitled Fundamental Physics. We continue with part 1, which is classical and fluid mechanics. As mentioned on module content, we are reaching unit 4, which is about work, energy, and power. As mentioned on the module content, we need to look at a general standard of work, power, kinetic energy of translational motion, work energy theorem, potential energy, law of conservation of total mechanical energy, and we will finish this unit with tutorial activities as well. Let us start with the work done by a constant force. Consider an object that undergoes a displacement r along a straight line, means the body starts from left and goes to the right and has moved a distance x. If you take this distance x times the unit vector along the x-axis, you get the vector displacement r, which is equal to xi. And we hear the force is acting on the body at an angle theta above the horizontal axis. This means that this is a force in a direction of motion, which is a pulling force. Meaning only this force is making this body to move such a distance. Then another force may be applied in a direction horizontal to x-axis by pulling the same body from initial position to a final position, and then the work done by a constant force F to move a body within a displacement r is equal to the magnitude of force times the distance moved times cosine of an angle theta. This means that the work done is equal to the scalar product between the force and the vector displacement. From this formula comes the unit of the work done as the unit of force times the unit of distance, because cosine of any angle varies between 1 and -1. Then the unit of the work is Newton meter, and another unit of work is equal to joule, where one joule is equal to 1 Newton meter. Then we have 1 joule as the unit of the work done is equal to 1 Newton force, which is acting on a body of mass m in order to move it through a distance of 1 meter. Then 1 Newton meter is equal to 1 joule. This is a fundamental equivalency between joule and Newton meter as a unit of work. We continue with describing what happens when the angle theta changes. When the angle theta varies between 0 and 90 degrees, the work done is positive, because the cosine of an angle in the first quadrant means an angle between 0 and 90 degrees is positive. And then when theta is positive, when theta is larger than pi over 2, means larger than 90 degrees, the work is negative. Remember, the work done is equal to the applied force times the distance moved is s, let us say s, times the cosine of an angle theta, where theta is an angle between theta, this theta is an angle which is between the applied force and the x-axis. Then if this angle theta, which is between the force and the x-axis is less than 90 degrees, the work is positive. And if theta is larger than 90 degrees, the work done is negative, because cosine of an angle larger than 90 degrees is negative. And the work done becomes 0 when theta is equal to pi over 2, because cosine of 90 degrees is equal to 0. Second, power. Power is defined as the rate at which the work is done. This means that as the work is related to energy, and once the work is done, the energy is transmitted to the body. Then this means that the power is defined as the time rate of energy transfer, or actually called the time rate of doing a work. Mathematically, we see that the power is equal to the change in watt per unit time, how the work is changing in unit time. And since the work, we know that the work is equal to the force. We know that the work is equal to the force times the vector displacement. Both are vector quantities. Then force scalar vector quantities. Then the change in work. This means equal to the force, because the force is constant. We are dealing with the work done by a constant force. Then scalar, the change in vector position. As this change is done by unit time, so the change of work per unit time is equal to the force times the change of vector position per unit time. And then we know that the change of vector position per unit time is equal to the speed. Then this is equal to the force scalar the vector velocity. It's the reason why it is said that the power is equal to the work done over the time. So you may say that the power is equal to the work done over the time taken, or the power may be equal to the force magnitude of an applied force times the speed. And according to the formula, the power is equal to the work over the time. Then the unit of work is joule and the unit of time is second. So the unit of power is joule per second, which is equal to watt, where 1 watt is equal to 1 joule per second. In British engineering, the power is measured in a unit called horsepower, where 1 horsepower is equal to 746 watt. Here we will use this definition in our calculations when converting the power in horsepower. Continue with energy by starting with kinetic energy and potential energy. Let us start with kinetic energy. First, let us define the energy. Energy is defined as an ability of a body to do a work. Once a body gains energy, the body does a work. Here we are dealing with mechanical work. This means that if a body gains an energy, mechanical energy, it means that it does a mechanical work. The mechanical work here is the motion of a body. It's the reason why we need to define two types of energies. The first one is kinetic energy. Kinetic energy is the energy related to the speed of a moving body, which means that kinetic energy is an energy associated with the motion, because the motion of a body is described by its velocity. And then mathematically, the change in work is equal to the force times the change in displacement. And we know that the force is equal to the mass times the acceleration. It's the reason why we need to replace the force by mass times acceleration. And we actually know that this acceleration is equal to the change in velocity with respect to the time, and this dx is equal to the velocity times dt from the kinematic equations, stating that the velocity v, that dx over dt is equal to the velocity v. This means that this dx equals to the velocity v times dt as well. Then this is the reason why we have replaced dx by v dt and the acceleration by dv over dt. You see that the numerator contains dt and the denominator has dt. This is the reason why they will cancel each other, and you remain with mass times the speed times the change in speed. And remember, on the left hand side we have the change in the work done. To find an answer to this equation, we need to integrate. Then integration on the left hand side gives the work done, which is equal to the mass. Mass is constant, but the velocity of the moving body changes from initial velocity to a final velocity. This v with index I means initial velocity, and v with index f means the final velocity. Then the work done equals m means mass times the integral of v dv from when the velocity changes from initial velocity to the final velocity. And we know the formula for integration. We know that integral of xn dx is equal to x to power n plus 1 divided by n plus 1. Then it's the reason why this definite integral will be equal to v squared over 2, then times the mass, changing v from vi to vf, which gives 1 over 2 mvf squared minus 1 over 2 mvi squared. And here comes the definition of kinetic energy, which is equal to the product of the half of mass of a moving body and the square of its speed. Then where kinetic energy symbolized by the letter k is equal to 1 over 2 times mass times the square of the speed. Energy is also measured in a unit called joule. Here comes a fundamental theorem that we will use in different problems. This is called the work energy theorem. The work energy theorem stated that the net work done on a particle by external forces is equal to the change in kinetic energy of the moving particle. This means that the network means the total work done, which is the algebraic sum of individual works, which is equal to final kinetic energy minus initial kinetic energy. Then the network is equal to 1 over 2 mvf squared minus 1 over 2 mvi squared. This is a fundamental theorem that everyone has to take by mind. After this, we need to continue with potential energy. By definition, the potential energy is energy related to the position of the moving body and to the type of forces acting on a body. We need to underline these two things: position and force. It's the reason why here the potential energy symbolized by letter U is equal to minus integral of the force times dx. Dx is the vector position. Then as we are familiar with bodies moving in atmosphere near the surface of Earth, such as bodies in free fall and projectile bodies, all bodies are under the action of a force of gravity, which is equal to mass times the acceleration due to gravity. Then it's the reason why their potential energy is called the gravitational potential energy, which is given by U equals mgh. If you want, here may put an index UGR, means gravitational potential energy. Gravitational potential energy, where this mgh is equal to the force of gravity that is acting on a body in free fall or a body which is in projectile motion, and h is the height at which the body is. And then here we may prove this formula. If we consider a body which is initially at a height y1 from ground level, and if this body is allowed to fall from this height y1 and reaches another height, another level above the ground, let us say the height y2, then we may calculate its gravitational potential energy at the new position. As the potential energy is equal to minus integral of the force times the vector position. Here the body is moving vertically, means along y-axis, because we know that always y-axis is the vertical axis and the x-axis is the horizontal axis. All bodies moving vertically are moving along the y-axis as stated in free fall. Then the minus integral from y1 to y2, because the body leaves a height y1 and reaches a height y2. Then the force that is acting on a body in a free fall is only the force of gravity Fg, which is equal to the mass times the acceleration due to gravity. And then we integrate dy from y1 to y2, which is equal to minus mgy2 minus mgy1. This gives minus gives positive. If you take minus times minus gives positive. It's the reason why the gravitational potential energy equals mgy1 minus mgy2. Then equals mgy1 times minus y2, where the gravitational potential energy equals mgh, and here we take h as the change in position, means the change in height, which is equal y1 minus y2. This is how we will calculate the gravitational potential energy. Elastic potential energy. Here we show energy changes in an elastic rubber, or later we may also consider energy in a spring. Let us consider a stretched spring. We consider that the displacement x is equal to 0 because the spring has its original or initial length. Once you apply a force on a spring, first you may apply force by stretching the spring. If the spring is stretched, we may measure the stretched distance, or which is stretched length, or the displacement x. And here the person who is stretching the spring is applying a force called FP, means the force of the person. And once the spring reaches the maximum stretch, it tends to retain its original size by acting or by applying a force Fs. This force Fs is called the force on the spring. This force on the spring is equal in magnitude and opposite in direction to the applied force, to the stretching force. And you may also apply a force on the spring by compressing it. This force to the left is a compressing force, and then it is equal and opposite to the force in a spring, because the spring always tends to retain its original size. And this force on the person is equal to the constant k times the stretched length. This constant k is called the spring constant. And this force on the spring Fs is called a restoring force. Restoring force means a force that the spring exerts on the acting body in order to retain its original size. Then it is equal to minus kx. It is equal and opposite in direction to the applied force. Then we here may calculate the potential energy in elastic bodies. We know that the potential energy U is equal to minus integral of the applied force times the change in position, and the ds or dx. Here the force here is equal to minus kx. It's the reason why here we have the potential energy equals minus fd minus integral f dx equals minus integral of minus kx d dx, because the force is the force on the spring equals minus kx dx. Then this is 1 over 2 kx squared. It's the reason why the potential energy in a spring or in elastic bodies is equal to 1 over 2 kx squared, where k is called the spring constant and is measured in the unit of force over the unit of distance, where k is positive. When it must be positive always. Then a force exerted on a mass attached on a spring, which is the one that extends the spring. Then the last one is the total mechanical energy. By definition, total mechanical energy of a system is equal to the sum of kinetic energy and potential energy. And here comes the law of conservation of mechanical energy, which states that the total mechanical energy of a system remains constant if the only force that does work is a conservative force. This means that at any instant, or let us say at the initial point or initial position, the total mechanical energy is at the initial position is equal to the total mechanical energy at the final position, which means initial kinetic energy plus initial potential energy is equal to final kinetic energy plus a final potential energy. Then once you are asked to announce or to state this law of conservation of mechanical energy, you need to say that the law of conservation of mechanical energy states that the total mechanical energy of a system remains constant, means unchanged, if the only force that it does work is conservative force. You may also consider this mathematical expression where initial total energy is equal to the final total energy, or the initial kinetic energy plus initial potential energy equals to the final kinetic energy plus final potential energy. And here we may define what is a conservative force. A conservative force is a force that does a work which doesn't depend on the path taken by the particle. Here, gravitational force and the spring force are examples of conservative forces. It's the reason why we have calculated the gravitational potential energy, and it's the one which is used in this formula for the law of conservation of mechanical energy. Then we may start with exercise number 1. Subquestion A. Steve exerts a steady force of magnitude 210 Newton on a stalled car in the figure below as he pushes it a distance of 18 meters. The car also has a flat tire. So to make the car track straight, Steve must push it at an angle of 30 degrees. We are given the applied force, distance moved,